Hello guys, so welcome back. In the previous video, we defined analytical chemistry. We also discussed the areas of analytical chemistry, and then I explained the importance of analytical chemistry. And lastly, we look into the different classifications of analytical methods. Now, in this video, I will discuss the steps in performing a chemical analysis. Okay, a typical quantitative analysis involves a sequence of steps as shown in the flow diagram. In some cases, one or more steps can be omitted. For example, if the sample is liquid, then we can avoid chemical dissolution step. Now, we will go through all of these steps in the succeeding slides. The first thing is that we have to consider is to know what specific information that we need to obtain. In other words, the analyst must be able to know the type of information that is to be obtained. Now, this is a basic requirement in all chemical analysis. This is an essential step as this will guide the analyst to decide as to the complexity of the analysis that has to be carried out. Remember that it is important that the analyst must be able to translate general questions into specific questions that can be answered through chemical measurements. For example, the local government wants to know if the sample of groundwater is safe for drinking. Now, the analyst can translate this general question into what is the level of organic contaminants that are present in the sample of water, or how much heavy metal is present in the groundwater. Now, these questions can now be answered through chemical measurements. The second step in all quantitative analysis is the selection of a method. Now, the choice is sometimes difficult and requires experience. Selecting the analytical procedure depends on the analyte and sample type. The complexity of the sample and the number of components in a sample always influence the choice of the method. Now, it is important that the analyst should consider the factors such as the accuracy and precision of the method, the required sample type and size, the analysis time, the analysis cost of the method, and the analysis expertise level. We have several compendium of analytical methods available for analytical chemists. The compendium contains analytical methods that have been defined and validated and are currently used by various regulatory laboratories. The examples are the AOAC, which is the Association of Official Analytical Chemists, or the official methods, ASTM, which is the American Society for Testing and Materials, USP, or it is known as the United States Pharmacopoeia, and the British Pharmacopoeia. These are publications that contains legally recognized standards of identity, the strength, quality, purity, packaging, and labeling for drug substances. It also includes dosage forms and other therapeutic products, including nutritionals and dietary supplements. The next step in quantitative analysis is to acquire the sample. Sampling is the process of selecting or obtaining a representative of the material to analyze. Now, in order to get a meaningful information, the chemical analysis must be performed on a sample whose composition should faithfully represent to that of the bulk, or in other words, the sample must have the same properties that are representative of the bulk of material from which it was taken. Proper sampling plans should be implemented depending on the type and source of the sample. For example, if it's a heterogeneous or homogeneous sample. When a bulk material is heterogeneous, then great effort is required to get a representative sample. Now, one way to solve this problem is to use a mortar and pestle to grind heterogeneous solids into fine homogeneous powders. Sampling is frequently the most difficult step in chemical analysis and the source of greatest error. Now, the final results of the analysis will never be more reliable than the reliability of the sampling step. So you have to be careful when you do sampling. Alright, so there are two reasons why sampling is significant. First is that there's a lot of chemical methods of analysis that are destructive in nature, which means that you have to dissolve or volatilize the sample. The destructive nature of this analysis means that it is difficult to recover the sample at the end of the analysis. It is often desired that a chemical analysis is non-destructive in nature so that you can preserve the sample after the analysis. For example, it is foolish to dissolve the entire gold ring if we just want to know if this is really made out of gold. The need for sampling also arises due to the limitation of the instrument and the analyst. Modern instruments for chemical analysis typically requires micro to semi-micro amounts of sample for analysis. As an analytical chemist, analyzing a large amount of sample is also exhausting. Now imagine, for example, you want to determine the percent salinity of seawater. It is impossible to use all water in the sea for this analysis. The next step in an analysis is to process the sample. Sample preparation refers to the conversion of the sample into a suitable form for chemical analysis. Under most circumstances, we must process the sample in any of a variety of different ways as summarized in this slide. Dissolution is the most convenient way for sample preparation, especially for solids. We actually dissolve them in liquid to form solutions. Concentration is the reduction or removal of the solvent to increase the quantity of the analyte, especially if the analyte is in trace amounts. Now, masking is making interference incapable of interfering with the analysis. The first step in sample processing is the preparation of laboratory samples. A solid laboratory sample is ground to decrease in particle size, mixed to ensure homogeneity, and stored for various lengths of time before analysis begins. Because any loss or gain of water changes the chemical composition of solids, it is a good idea to dry the samples just before starting the analysis. Or alternatively, the moisture content of the sample can be determined at the time of the analysis in a separate analytical procedure. Alright, so for liquid samples, we have to remember that the solvent in liquid samples can evaporate when they are allowed to stand in open containers. If the analyte is a gas dissolved in a liquid, the analyte must be kept inside a second sealed container to prevent contamination of, let's say, atmospheric gases. Now, extraordinary measures, including sample manipulation and measurement in an inert atmosphere, may be required to preserve the integrity of the sample. Now, once we have the sample prepared and converted the analyte to an appropriate form of the measurement, the next step is to eliminate interferences. Now, what are interferences? Interferences are other species that in the analyte that can affect the measurement. These species can increase or decrease the response of the analytical method and makes it appear as if there's more or less analyte than it actually present. It is important that a scheme must be made to isolate the analytes from interference before the final measurement can be made. Now remember that there is no hard or fast rules to eliminate interferences, but we have several ways to remove them prior to the chemical analysis. In some cases, selective precipitation can be used to remove interferences from a mixture. You can do this one by addition of an appropriate reagent that may convert interfering ions into precipitates, which can be easily filtered off. Or you can also remove interferences by carefully controlling the pH in order to precipitate other interference. Now, the precipitates can be physically separated from the mixture by filtration or simple centrifugation. In masking, a complexing agent is added, and if the resultant complexes are sufficiently stable, they will fail to react with the reagents added in a subsequent operation. We will learn more of this technique when we discuss complex formation reactions in Module 2. Another method to eliminate interferences is by selective oxidation or reduction. Now, selective oxidation or reduction happens when the sample is treated with a selective oxidizing or reducing agent which reacts with some ions present. We will learn more of this when we discuss redox titrations in Module 2. The next step in analysis is the analysis proper. This time we can now use the method that we chose to our prepared laboratory samples. In doing the actual analysis, we measure or determine the concentration of the analyte in several identical portions known as alico. Replicate measurements is usually done to ensure the reliability of the data. When I say replicate or replicate samples, these are portions of the materials of approximately the same size that are carried out through an analytical procedure at the same time and in the same manner. Even the best method, however, may not be free from interference that contribute to the measured signal. Potential interference may be present in the sample itself or in the reagent used during the analysis. Blank samples are used to confirm that the analytical system is free of analyte contamination or interfering substances. We have several types of blanks that I will discuss in the next slide. Method blank contains all components except the analyte, and it is taken through all steps of the analytical procedure. Remember, blank does not contain any analytes. You can prepare the method blank sample using the same glassware, solvent system, reactant dilution schemes, and other preparation steps through which the analytical sample is taken, but without adding any analytes. A reagent blank is similar to the method blank, but this is not been subjected to all sample preparation procedures. And lastly, field blank is similar to the method blank, but it has been exposed to the site of sampling. Now, the next step in an analysis involves calculating the analyte concentrations from the experimental data. This is very easy with the aid of calculators and computers. In reporting the data, the analyst should have a proper documentation of procedures and results obtained. Now, this strengthens the claim of validity and the reliability of results obtained from the analysis. This is also the reason why you need to have a very good laboratory notebook. The report might be written to be read only by the specialists, such as, for example, your instructors, or it might be written for a general audience, perhaps your mom or your dad. The analyst should ensure that the report is appropriate for its intended audience. The analyst must also provide some measure of uncertainty with the computed results if the data are to have any value. Remember that results are valid only if these were obtained from replicate measurements and if the data were treated statistically. Finally, in drawing conclusions, the analyst should consider the limitations of the analytical method used. The analyst must understand that all analytical methods have inherent strengths and weaknesses. Once a report is written, the analyst might not be involved in what is done with the information, such as modifying the raw material supply for a factory or creating new laws to regulate food additives. The more clearly the report is written, the less likely it is to be misinterpreted by those who use it. Obviously, the data must be presented clearly and objectively as to not to cause any misinterpretations when formulating a conclusion. Alright, so this is the final slide for this lecture video. In this lecture video, we've learned the different steps and important aspects in performing a quantitative chemical analysis. In the next video, we will now have a review of the basic skills that an analytical chemist must possess. That is, a knowledge of chemical stoichiometry. Again, thank you for watching. Bye.